let's take a look at more about nuclei and nuclear radiation. So it turns out that just as electrons exist in certain allowed energy levels, remember this picture, nuclei also exist in certain allowed energy levels. So for example, americium-241 will decay into neptunium-237. But this decay can follow different paths. And to express this, I'm going to draw a diagram here. So here's the unstable americium-241 nucleus. I'm drawing this starting energy level up here. And it can decay, or it will decay, into a stable ground state of neptunium-237. But it turns out that neptunium-237 has three energy states. The nucleus has three allowed energy states. So these two that are above the ground state, they are less stable states of neptunium-237. They're states where the neptunium-237 has more energy. So the americium-241, in order to decay into the neptunium-237, it has to emit an alpha particle at some point. And let's take a look at the different ways that that can work. Well, the americium-241 can go to this high energy state of neptunium-237 by emitting a relatively low energy alpha particle. So an alpha particle comes out, but it has less kinetic energy. And then this unstable neptunium-237, it can decay into the stable ground state of neptunium-237 by emitting a bundle of energy, by emitting a gamma ray, right? And it does that, and the neptunium-237 remains neptunium-237 because the gamma ray doesn't remove any charge or mass, just energy. Now, another path that the americium-241 could take when decaying is it could emit a higher energy, a medium energy alpha particle, so an alpha particle with a little more kinetic energy to it, and then a lower energy gamma ray by following this path. Or the decay could take the form of a single high energy alpha particle and just go straight from the americium-241 to the stable ground state of neptunium-237. And then it emits a fast-moving alpha particle, a high-energy alpha particle. So just like electrons can only jump between levels and emit and absorb certain photons, nuclei can only emit alphas and gammas with specific energies which are determined by the nuclear energy levels. Now, notice I didn't mention beta radiation, but that's because beta radiation is a little different. We'll look at that in a moment. But let's look at alpha decay in a little more detail. So according to classical physics, when I say classical physics, I mean not quantum physics, an alpha particle shouldn't be able to escape a nucleus. Alpha particles shouldn't have enough energy to be emitted from their nucleus. So I'm going to draw kind of a model of a nucleus here. Here are the nucleons inside of the nucleus. They're trapped inside of this well. If you can imagine that the nucleus is kind of a trap or a well that the nucleons are stuck in. And there's these sort of walls or barriers that the nucleons have to get through in order to get out of the nucleus. Now, inside the nucleus, especially very large nuclei, the nucleons tend to form these little bundles that are two protons and two neutrons. Or in other words, they form little alpha particles within the nucleus. Now, I'm oversimplifying things a little bit, but that's kind of what happens in these large nuclei. So like in uranium-238, the uranium-238 has lots of these little cliques of two protons and two neutrons floating around inside the nucleus. And that's because that combination of two protons and two neutrons is very, very stable. So this little nugget of two protons and two neutrons exists within the larger nucleus. Now, because of quantum mechanics, these little alpha particles within the nucleus, they actually have a probability of showing up outside the nucleus. And one way to think about it is, if we go back to the idea of the wave function, the alpha particle's wave function has a non-zero value outside of the nucleus. In other words, this is tunneling. The alpha particle can tunnel through this barrier, and the alpha particle has a non-zero probability of showing up outside of the nucleus. And if it does that, then it has escaped. and it's able to leave the nucleus, and it's emitted by the nucleus. So tunneling explains how alpha particles are emitted by nuclei. All right, now let's look a little more deeply at beta decay. So in beta decay, what's observed is that the emitted electron or positron will not have specific energies. So when we looked at alpha particles and gamma particles a moment ago, we said that they have to correspond to the energy levels, the differences in energy levels for nuclei. But when we observe the electrons and positrons that are emitted in beta decay, that's not true. So, for example, if you look at the kinetic energy of electrons that are emitted in the beta decay of bismuth-210, those emitted electrons have a range of kinetic energies. And it's a distribution like this. So there's, more likely kinetic energies that show up and less likely kinetic energies of those electrons. But there aren't specific energies of those electrons, which is different than the alpha and the gammas that we looked at before. Alphas have to have specific energies, and gammas have to have specific energies when moving between these nuclear energy levels. So why is beta decay different? Well, for a while, no one knew. Until eventually someone proposed that, hey, maybe there's something else that we're not seeing that's carrying away some of the energy. And if there's something else that we can't see and detect that's carrying away some of the energy, maybe the positron and that other thing, or the electron and the other thing, depending on the type of beta radiation, maybe the combination of energy of the electron and other thing, or positron and other thing, has quantized energy values. And it turned out that was the correct answer. There is something else besides the electron and positron that's emitted, and you already have seen that. When you emit an electron in beta radiation, you also emit an anti-neutrino. And when you emit a positron, you emit a neutrino. That neutrino is also carrying away some of the energy that's emitted by the nucleus. And it turns out if you add together the energy of everything that's escaping, so the electron and antineutrino, or the positron and neutrino, the total energy emitted is quantized, or does have specific total amounts of energy that correspond to the energy changes in the allowed energy levels of the nucleus. So the reason that this distribution exists, the reason that there aren't specific energies of the emitted electrons or positrons, is because you also have to take into account the neutrino or antineutrino that's emitted. Now let's take a look at radioactive decay in a little more detail. So remember, the decay of a single nucleus is a random process. It cannot be predicted exactly when a single nucleus will decay. But we can quantify the behavior of a population of nuclei. If we have many, many nuclei of the same type, we can quantify the statistics of their decay. And to do this, we're going to bring in a couple ideas. One is the idea of something called activity, which is represented with a capital A. And activity is defined as the number of decays occurring per second in a sample. And we're going to define another constant called the decay constant, which is represented with the Greek letter lambda. And the decay constant is found in this equation. The activity is equal to the decay constant times the number of nuclei present. So this decay constant is the ratio of the activity of a sample to the number of nuclei within that sample. And every different nuclide will have a different decay constant. So the decay constant depends on the type of nuclide you have. Now, one other thing. The activity can be written as the rate of change in the number of nuclei. In fact, it's the negative of the rate of change in the nuclei. And to sort of illustrate this, think about a sample that has a very high activity. So that means that there's many radioactive decays occurring each second. Well, What that means is that the nuclei are very rapidly becoming some other type of nuclide. So the number of nuclei in your sample is rapidly decreasing. Right? And if you had a low activity sample, then that would mean that you're slowly turning your nuclei into a different nuclide. You're slowly losing the original nuclei that you had. So yeah, the activity is the negative of the rate of change in the number of nuclei in your sample. And using this fact, now we can get a nice little equation that has a derivative over here and then that same variable n over here. And we'll do a little calculus to solve this. So let's see, dn dt is equal to negative lambda n. Well, then dn over n is equal to negative lambda dt. And now we'll take the integral of both sides. And if we take the integral from time 0 to time t, which means we're going from the number of nuclei we had at the beginning to the number of nuclei we have at the end, get a couple dummy variables in there, and then we get a natural log of n minus the natural log of n0 is equal to negative lambda t. Do a little natural log identity here, do a little algebra, and then we can solve for n. n is equal to n0 e to the minus lambda t, where n is the number of nuclei that are left after time t. n0 is the number of nuclei that were there at the beginning at time t equals 0. And then t is the amount of time that passed, and lambda, of course, is the decay constant. Now, we can also change this a little bit. Let's say we want this in terms of the activity. Well, the activity at some time is equal to lambda times the number of nuclei. So it's equal to lambda n0 e to the minus lambda t. Okay. Now, it might be helpful to relate this to the half-life. We thought about the half-life in a previous unit. So half-life is the amount of time it takes for half of the nuclei to decay, right? So let's see. If we start out with this equation we have, n equals n0 e to the minus lambda t. Well, after one half-life has passed, we should have half of the number of nuclei we had at the beginning. So that means the number of nuclei we have at the end is n0 over 2. Half of the remaining nuclei. And the amount of time that has passed in this situation is a half-life. So now we have a nice equation, and we just need to solve for the half-life. And if we do that, it takes a little bit of math. You got to take a natural log, yada, yada, yada. And then, okay, one half-life is equal to 0.693 over the decay constant. So that's the relationship between the half-life and the decay constant.